Muchas gracias, Alberto, por la presentación. Bueno, aparte de darles la bienvenida, quería comenzar comentando un poco de dónde sale la iniciativa de estas charlas. Yo soy coordinador de posgrados de la Escuela de Ingeniería Mecánica de la Universidad Industrial de Santander y formo parte de la Red Colombiana de Investigación en Fatiga y Fractura, que pues ha nacido recientemente como una iniciativa para encontrar espacios comunes de investigación entre la universidad y las empresas. Allí en la diapositiva pues, ustedes ven una imagen de los participantes en esta red con un fuerte balance entre el desarrollo de teoría y estudio académico y la contraparte industrial, que pues finalmente son los que están llamados a aprovechar estos avances y este proceso de apropiación tecnológica. En particular, en la Escuela de Ingeniería Mecánica de la UIS hemos tratado de incentivar este tipo de actividades, las redes de colaboración, todo dirigido a, por un lado, pues mejorar los indicadores de investigación de nuestra región, pero también a realizar ese proceso de transferencia que tanto hace falta en el tejido productivo. El día de hoy pues vamos a iniciar este ciclo de conferencias como comentaba Alberto, con un investigador muy cercano a nosotros, Sundar Natarajan, que es profesor asistente del Instituto Indio de Tecnología en Madras. Él trabaja junto con otro grupo de investigadores en el Legato Team y en particular pues a través de la escuela hemos realizado la gestión para dar comienzo a esta red de conferencias de la Red Colombiana de Fatiga y Fractura. Entonces, pues es para nosotros un placer tener aquí el día de hoy a Sundar. Él nos va a comentar aspectos referentes a la mecánica de la fractura y cómo se está tratando este tema desde el ámbito computacional o mediante el uso de métodos numéricos. Antes de comenzar, pues hacer una presentación formal del conferencista. Él es profesor asistente desde el 2014 en la sección de diseño de máquinas del Departamento de Ingeniería Mecánica del Indian Institute of Technology, Madras. Esta universidad está clasificada entre las primeras 300 universidades del mundo y es la primera universidad en ingeniería en la India. Pertenece a una red de universidades de alto desempeño académico y, bueno, tiene un amplio reconocimiento en Asia. En particular, el profesor Sundar Natarajan es un investigador que tiene más de 135 publicaciones indexadas en Scopus, con un factor de impacto H-index de 34, y él ha estado dirigiendo su investigación en temas relacionados con mecánica de la fractura, métodos numéricos avanzados para la resolución de este tipo de problemas, que es el propósito de la charla. Aquí hablarán de XFEN, Facefield y otros similares. También tiene publicaciones muy reconocidas en el ámbito de materiales compuestos y materiales funcionalmente graduados. En su experiencia, pues él estuvo trabajando varios años en General Electric, en la división de aviación, como ingeniero. Posteriormente estuvo trabajando en Cardiff University, en la Universidad de New South Wales y en el Instituto Indio de Ciencia en Bangalore. Con esto, pues, darle nuevamente la bienvenida a Sundar. It is very nice to have you here with us. I hope we can continue our collaboration, and I can now give you your time for the speech. La presentación para los asistentes se realizará en inglés. Pueden activar el closed captioning de Google Meet, por eso escogimos esta herramienta. Y adicionalmente, si tienen dificultades en seguirla, también pueden activar la traducción de esos subtítulos en el video, ¿de acuerdo? Entonces, bueno, con esto yo creo que ya podemos comenzar. Sundar, are you there?
Yes, I'm very much here. Can you see
Okay,
my...
so now I'm going to start sharing my presentation, and I'll give you space to share yours and start with the talk. On behalf of the Colombian Network of Particle Vector, we would like to thank you again, also Universidad Industrial de Santander, and we hope we can continue collaborating with your university in the near future. Thank you for accepting our invitation, and you can present now.
Good morning, everyone. Thank you for this great opportunity, and I hope everybody is safe and sound with your family amid this pandemic situation. Am I audible?
Yes, you are.
Okay. All right. So thanks for giving me an opportunity to present my work at Columbia Network for Fracture and Fatigue. And it's my great pleasure to talk about some of the research activities that I have been doing here at IIT Madras. Some of them have been started during my PhD work, and during my postdoc, something else I picked up. So I'll be giving a short overview of different techniques that or methodologies that we are working on for modeling fracture in this talk. So let me start presenting my screen. Let me know if you're able to see my screen.
Yes, we can see your screen now.
Okay, thank you. So the title of today's talk is going to be on recent advances in computational fracture mechanics. I'm Sundarajan Natarajan. I'm a faculty in the Department of Mechanical Engineering at Indian Institute of Technology, Madras. And that's my recent picture. The picture that you saw and the invitation is quite old. And this is how I look now. Once again, thank you for the great opportunity. So this is where I am currently located. Actually, I'm in the south of India. And hopefully, pandemic situation becomes better, and hope to visit Colombia sometime. It's been a really long time. I think last time when I met Andres, that was in 2018 at WCCM in the US. So hope to visit you in the near future. So I'm going to start my talk by giving a quick overview of Indian Institute of Technology. So this is one of the premier institutions in India. This was established in 1959, and it's currently ranked #1 in India. We have around 550 faculty members, hosting around more than 8,000 students. The beauty of this is that it's amidst a forest. So there is a 250 hectares of forest campus. So both campus, the students and the faculty reside on campus. There's a nice picture of the bee on campus. We have 9 engineering departments, traditional departments like civil, mechanical, and electrical. We also have aerospace, chemical, computer science, engineering design, metallurgy, and ocean engineering. We also have 9 other allied departments: applied mechanics, physics, mathematics, chemistry, humanities, and management studies. And I belong to the mechanical engineering department, where we have 6 research focus groups. We are around 65 faculty members with around 350 undergraduate students and little more over 500 master students, which are basically MTech students. And we also have little over 500 research scholars. So we have 2 types of research programs here at IIT Madras. One is the traditional doctoral program. We also have Masters of Science by Research, where the student is expected to do original research as a part of their master's program. And there are 6 research groups: Advanced Computational Engineering, Materials and Design, Manufacturing Science and Engineering, Dynamics, Acoustics and Controls, Energy Science and Engineering, and Micro Nano Bioscience and Engineering. Although I sort of fall into all the research focus group, my primary focus our affiliation is towards the first focus group, which is computational engineering. We also have specialized centers for rehabilitation devices, non-destructive testing, and also on combustion research, which is like unique in India. So all said about my institute. This is my research group. We have a small 9-member group with 1 postdoc, couple of Master of Science by Research, and the rest are PhD scholars. Most of them have graduated, so this is really a bit old picture now. But nonetheless, they are still active part of the research group. We are still working on some problems that we started during their work here at IIT Madras. And before I start my presentation, I'd like to thank my collaborators. The first one is my PhD supervisor, Stefan Bodes, postdoc mentor, Chongmin Song, other collaborators from across the world, Timo Drabzuk, Yanta Rui, Caroline Burke, Hung, Elena, and Antus, who have been associated since we met in Cardiff in 2011, I believe, 2010. All right, so let me start my presentation by giving a research vision. You see 3 pictures here on this slide. The extreme left is, could be a melting or a solidification of an ice or water. The one that is at the center is, a crack propagation, either due to a static loading or a dynamic loading or a fatigue loading in structural members or engine metals. The last picture on the extreme right is a picture about showing how a flame propagates in a fuel or in a combustible medium. Although they come from different physics, they depict different physics. There is one common phenomena that is existing across these physics. The common phenomena is that there is an interface, and this interface evolves in time, right? So if you look at the first example, there is a solid-liquid interface which sort of evolves in time due to certain physics, governing physics. In the picture at the center, you have a crack phase. Due to some external loads, this crack phase starts to propagate. So there is an interface that moves in time. The same applies to the last case also, where there is a flame front, which evolves or changes its shape due to certain other conditions. So my research vision is to look at the centrality of a mathematical formulation across the discipline so that we can have an impact on a variety of fields. So predominantly my focus is not specific to one class of problems, say solid mechanics, but I look at general differential equation and see how I can solve them efficiently using computers. And in particular, I'm interested in looking at moving boundary or free boundary problems because they have wide applications in a variety of fields. For example, you can try to simulate baking of a cake to a tumor growth. It could also be used for assessing damage in complex structures. So my interest is to come up with common building blocks which can help us make progress in a range of disciplines. Okay? Although today my focus would be mostly on metals and how crack growth can be modeled using some of the new techniques, but a similar framework can be adopted to other physics, for example. So computational mechanics, as we know, has revolutionized the design, so it can probe into areas where theoretical or experimental investigations are difficult. So it is applied to civil, structural, biomedical. It's also used in finance modeling. You name it, computational mechanics has a role to play now. And a typical framework is what is shown here, is that let's say that you have a physical problem, and this physical problem is discrete in nature, and we try to understand what is going on with this physical problem. The way we do it is to get help from mathematics. So we seek help of a mathematical modeling and observe the physical formula and convert that into a set of differential equations. And hope that by looking at the solution of the differential equations, we can interpret or understand the physical problem. For example, if I'm looking at the stresses in the turbulent blade, I would pose this as a set of differential equation and then try to solve this differential equation to understand the response, for example, that is shown on the extreme right with the color counter plot. But the problem lies in solving this differential equation. So these differential equations are continuous form, and for complex structures, complex boundary conditions, there is no way you can get a closed form solution. And that's when we go back and look at, use numerical techniques to solve these differential equations. And the primary goal of these numerical techniques is to convert these differential equations, which are in a continuous form, into a set of algebraic equations. And then we use algebraic, concepts from linear algebra to solve for the numerical solution, right? Because we want to use computers to solve it, and computers works with numbers. So that's the reason why we do it. And there are a variety of methods which are currently in use, which help us solve these differential equations. And since all of them are approximation techniques, each have their own advantages and disadvantages. So I've listed some of them here, like finite elements, least square, finite volume method, spectral element method, boundary element method, collocation, finite difference, Ritz-Galerkin, and so on and so forth. And of these, for solid mechanics problem, finite element is the most sought out because of its strong mathematical background, its robustness, and there is almost 3 decades of research that has gone into finite elements, which is now widely accepted by industry also. We have sophisticated commercial softwares, robust commercial softwares like Abacus and ANSYS, the results of which can be trusted. But the whole idea is, we should keep in mind, is that the role of numerical simulation is not to replace experimental observations, but to help understand what we observe experimentally, or to reduce the number of experiments that we would have to do, come up with a design which is feasible. So if I want to pose this in a mathematical framework, the governing equations are given by differential equations. So like I said, a differential equation. So where LU equal to L equal to F, that's on the domain. L is some differential operator. And we invoke concept of Galerkin, and then we try to write the equivalent weak form for it. And then we try to find the solution, which is the approximate solution in terms of some polynomials. So this is a mathematical framework. And simple words, what we do is we try to divide the region into smaller regions, right? So for example, if I'm trying to look at some physics over a circle, I divide the circle into smaller regions. So the simplest region could be a triangle. It could also be quadrilaterals or polygons. But these have to be non-overlapping. For example, that is most used method. And by assuming the solution over each of these smaller regions, we can now construct the global solution. That's how it works. And the same idea also works in case of 3 dimensions, where the domain can be discretized or divided into non-overlapping elements. So the standard elements that are used in 3 dimensions are tetrahedrals or hexahedral elements, which are 6-sided or 6-faced elements. And the typical process in design is that you have a CAD model, and this CAD model is not suitable for analysis because this has complex shapes, and then it's not suitable for analysis. So what we do is we spend a lot of time converting the CAD model to analysis suitable model. This process, we call it as meshing, and many times meshing is the most expensive step in this whole process. And once you have the mesh, then you can adopt any of the previously said approaches to find the solution over this domain. And if it is not feasible, then you go back fixing the CAD model. And this is a typical cycle for design evolution. However, finite element is very robust. It's commercially acceptable. There are some setbacks with finite elements. I've listed some of them here, which are more critical than the rest. For example, the regions that we try to discretize have to have some nice qualities, properties of it. the foremost property is that the elements cannot be concave. For example, it doesn't allow elements to have concave regions because then the finite element breaks down. Or it cannot have very long elements which loses some good approximation properties. Although we may start with the good quality element, because of the theoretical framework, for example, if you're trying to solve a large deformation problem, we may end up with elements which are badly shaped, and then the analysis breaks down. So we have to stop the analysis, do something called a remeshing, and then start the analysis again. So that is a bottleneck if you're trying to use finite elements. And the other problem with finite element is that it requires conforming mesh to represent internal boundaries. And since we are using polynomials to represent the solution, if there is a sharp gradient or a singularity, finite elements sort of struggles to represent it. And we need extremely refined mesh close to the singularity. For example, you can see there is a red mesh here where the mesh is really fine, which is required to capture the singularity there. And also, you need to have a conforming mesh. For example, the black lines could be a representative grain, for example, if you're talking about polycrystalline materials. And you need to have a mesh that sort of conforms to these grains. And if these grains start to change shapes or evolve, I would have to update my finite element mesh, which sometimes could be not a trivial task to do. The last of the difficulty that I mentioned here is to do with geometry representation, because we use polynomials to represent it, and many times polynomials are not good at representation of actual engineering structures. For example, if you have really complicated shapes like this, you can see that the geometry is not exactly represented, and this introduces errors in your simulation. And as a stress analysis, we should be aware of these pitfalls of the finite element method. But this also has opened up a lot of research in trying to improve finite element method, right? And finite element method has also been used to understand material failure. So material failure could be an advantage or a disadvantage. So in this slide, I'm trying to showcase where it is not beneficial to have a material failure. And it's so important to understand when and how a material would fail. And if you're able to predict it, it's going to save a lot of monetary benefit. It will also save a lot of huge human life. And in this case, understanding damage mechanisms can help us design a structure which is damage tolerant. So we can avoid certain failures which are otherwise inevitable. Of course, understanding damage mechanisms also help us come up with a better tool design, so that we know what tool to use, to manufacture certain component, right? Because we should be able to remove materials or drill holes in certain materials, for which we need to understand how the damage mechanisms appear in certain materials. So a conventional finite element method would require, like I said earlier, a conforming mesh. So here I'm showing two examples. The one on the extreme right, where you see a red line. This could represent, for example, a crack. And let's say this is subjected to some loading. It could be a tension or some fatigue loading. If we were to use finite elements, every time the crack moves, we would have to update the mesh, which could be not a trivial task, especially if you're talking about multiple cracks, especially in 3 dimensions. This is an example of typical example where it could be a phase change problems, like what we've seen in a solidification problem, where you have 2 different phases, and then this orange line depicts the interface of these 2 phases. And with change in time, the shape of the interface changes. And if you were to use finite elements, we would have to update the mesh every time it changes. And updation is not the only key. We will also have to port the information from the previous mesh to the new mesh for subsequent analysis, which may introduce certain errors in the simulation. And like I said, this has opened up a lot of research activities to come up with efficient techniques to model these moving boundary problems with finite elements. Yeah? And in, like I said, in this talk, I'll focus more on fraction mechanics. There have been a lot of work on improving or using finite elements to solve crack growth problems in materials. The first one is based on remeshing finite element, the one that we saw in the earlier slide, where the mesh is updated every time the crack grows in time or changes shape, right? Early 1990s, there was this method that was introduced called the extended finite element method, which is now also available in Abacus as an add-on, which the beauty of this method is that it doesn't need a conforming mesh to capture the crack growth. So the crack can independently grow on a background mesh, right? So that is the beauty of it. There is also this formulation called peridynamics, which works on integral formulation, which is also currently being heavily researched on to model fracture growth. And late 2000, there has been this idea of using phase field method, which is originally used for modeling phase change materials. Now people are trying to use phase field models to model crack growth in materials. Right? And in today's talk, I will focus on 3 topics: extended finite element method. I'll briefly touch upon a method called scale boundary finite element method, which has some nice advantages. And lastly, I'll touch upon phase field method to show. So the first of the topic is going to be on extended finite element method. So this comes under a bigger umbrella of methods called partition of unity method. And here the idea is to detach geometry and analysis. Remember, we talked about finite element method requires a conforming mesh. So now here the whole idea is that is it possible to come up with a method where the geometry can be independent of the mesh, and that's how the extend works. So the basic idea was. Excuse me, is there a question?
No, you can continue, Sundar.
So the objective of this is that if I have an interface, for example, a circular interface or some flower-shaped interface or a crack shown by a solid black line, is it possible to represent them independent of the mesh? Not only represent them, but I also capture the underlying physics, which is without a mesh that conforms to it, right? And conventional finite element would require that you need a conforming mesh. For example, if I'm trying to solve a crack problem, I need to have singular elements which are aligned to the interface, and you also need to have extremely refined mesh close to the crack tip so that you can capture the singularity. Remember, finite element works with simple polynomials, and polynomials are not really good in capturing the singular functions. Although if it is a static crack or a static interface, coming up with a mesh is not a problem, even in 3 dimensions. But the real problem comes when you have these interfaces that start to change shape or evolve in time. And this becomes computationally expensive if you are talking in terms of 3 dimensions, or if you have like multiple cracks, right, or multiple holes or inclusions. And conventional finite element method would have to differentiate a hole and an inclusion, whereas in XFEM, they can be treated in a unified way by just using appropriate AND-sorts or enrichment functions, which you will see in a couple of slides coming from now. And it's very robust in that sense. It can also model crack growth. It can also have these cracks coalesce, branch, it can do all sort of things with a mesh that doesn't update every time. All right, so when do we need enrichment technique? So we need enrichment techniques when you have discontinuities in your model, for example, cracks or metal interfaces. If you have large gradients like yield lines or shock waves, or if you have singularities, for example, not just cracks, or if there is a re-entrant corner, or if there is a boundary layer in your problem, like it could be a fluid-solid or a fluid-fluid interactions, or if you're solution is highly oscillatory. For example, if you're trying to solve a Helmholtz equation and looking at mid-frequency or high-frequency problems where the solution is highly oscillatory, and we know that a typical number of elements that is required to capture is that you need at least 10 elements to capture the wavelength. So now if I'm looking at a really high frequency, my computational expense just grows exponentially. But by using XFEM, we can, we don't have to use such a highly refined mesh, but still capture the essential physics of the problem. And the basic idea is that we will add certain functions to finite element basis that can capture the necessary physics. Okay, and the basic idea behind that would be to improve the convergence rate, because when you use finite elements to solve these problems, the optimal rate of convergence reduces by 1/2 for certain cases. So we would want to retain optimal order of convergence with finite elements, at the same time capture the necessary physics with a mesh that doesn't conform to the geometry. That's a whole objective. So this is one example how people try to model cracks. For example, they use what is called a quarter point element, which is a special case of an 8-noded serendipity element, where they place the crack tip on one of the nodes, corner nodes, and they move the mid-side node to 1/4 of a distance from the crack tip. And by doing this, we can capture the singularity that is present at the crack tip. But this works for isotropic homogeneous material, but for other cases, it doesn't really work that efficiently. So that is also one reason why there has been a lot of research in coming up with methods that can capture the physics of the problem. For example, if it is a bi-material interface and then you have a crack between those interfaces, the singularity is complex. So this sort of an arrangement does not work in favor of that. So again, like I said, there has been a lot of work in trying to improve finite element method, and I've classified them into 3 categories. They all come under a category called enrichment techniques. So one is called a local enrichment, global enrichment, and there is something called a mesh overlay techniques. The basic idea in all of these is to have a method where I can model these cracks or discontinuities independent of the mesh, right? And in this talk, I'm going to focus only on XFEM, although the same sort of a framework can be talked in terms of generalized finite element method or elemental enrichment techniques and other techniques. Okay, so the basic idea in XFEM is that you have the standard finite element basis function, and to it you add certain functions that carry the necessary information of the problem, right? So we don't know a priori what these functions are, but I know that if I can put in these functions, I can capture the physics of the problem. So for example, the first term, which is shown in blue color, that's a standard approximation for your unknown field. The one that is shown as PU enriched is the new function that we are going to add to the standard finite element basis. So here phi j's are standard finite element functions. Psi i's are the functions which carry the necessary local information of the problem. So if I'm trying to solve a